Hey everyone, in this video we're going to be talking about cubic spline interpolation theory. We're going to begin with a brief overview of spline interpolation, define what cubic spline interpolation is, speak about why it is used, and then lastly we'll walk through how to implement a cubic spline interpolation. Cubic spline interpolation is a powerful technique used to approximate a smooth curve that passes through a set of data points. Similar to the linear and quadratic splines that we have talked about in our past few videos, it breaks down the data range into smaller segments. However, we are now going to fit a cubic polynomial to each section. And this ensures continuity and smoothness at the connection points, which is something we were lacking in both the linear and quadratic splines. So, let's imagine that we have a system where we are tracking the amount of time that it takes to fill a bucket. As you can see, we are given 5 discrete data points, but we are interested in making a function that passes through all of our relevant data points. There are various types of spline interpolation, as we have talked about, including linear and quadratic. In brief, a linear spline interpolation simply connects our data points using straight lines, or a first-order spline, which, although simple, tends to lead to inaccurate interpolations as there is no curvature in our function. Secondly, a quadratic spline fits a second-order polynomial to our interpolation function, and this adds curvature to our interpolating function, but we only have one degree of freedom, which forces us to use parabolas and parabolas alone. Now we will talk about the most common type of spline interpolation, that being cubic spline interpolation. Unlike the quadratic splines, what makes cubic spline interpolation powerful is that it ensures continuity and smoothness at the connection points. This means that the curve and its derivative up to the second order are continuous throughout the entire range, whereas in quadratic spline interpolation, this is only true for the first derivative. Now, let's explore the benefits of using cubic spline interpolation. Firstly, it provides a more accurate representation of the data compared to simpler interpolation methods. The smoothness and continuity properties ensure that the interpolated curve captures the overall trend without excessive oscillations. So now that we have an idea of why cubic splines are useful, let's talk about how to use cubic splines. So, between each connection point, we are going to have a third-order polynomial, that being a cubic spline. So, imagining a set of data that looks like this, each point that we wish to interpolate through will be described as the following general cubic polynomial. Therefore, this will create a set of polynomial equations that look like this that we need to solve the coefficients for. And we will have n equations. Now all we need to do is develop a methodology for how we are going to solve for all of these unknowns. The first thing we need to do is determine how many unknowns we actually need to solve for. Well, as you can probably imagine, the number of unknowns that we need to solve for depends on the number of cubic splines that we are interpolating for. Therefore, we can say that for every spline n, we will have 4 n unknowns, meaning that we need to find 4 equations per spline that we add. Let's try to find our 4n equations. Firstly, we will have some known data points. These are the input-output pairs that we are interpolating through. Because each data point will share a spline, we actually get 2n equations. Therefore, we just need to find 2n more equations to be able to begin solving our system of equations. For our intermediate data points, we can define continuity and say that the first derivatives need to be equal. This statement will be true at every interior data point that we have, and this will give us n-1 equations. Therefore, we are missing n-1 equations still. Likewise, we know that we actually want our interior data points to also have equal second derivatives as we want our splines to be as smooth as possible. Therefore, this is going to be another n-1 equations. This leaves us with -2 equations. We have some options at this point. However, the most common way to find these 2 missing equations is through making some assumptions about the endpoints of our piecewise spline function, much like we did for the quadratic spline interpolation. The first common approach is a natural cubic spline, which ensures that the curve is continuous and has 0 second derivatives at the endpoints of each interval. Therefore, we get two equations by setting our first and last data points' second derivatives to 0, whereas a clamped cubic spline requires some extra data. We specify the slopes, the rate of change of the curve at the first and last data point. These slopes are called the clamped conditions. By providing these clamped conditions, we ensure that the curve has the desired slope at the endpoints, which can be helpful when we have prior knowledge or constraints about the behavior of our curve. It is worth noting that these are not the only two ways we can find our missing equations. They are just the most common. Other variations do exist, but they'll find two equations through playing with various boundary conditions and constraints. Lastly, all you need to do is solve your system of linear equations, which we have talked about plenty in the past. Hey everyone, in this video, we're going to be walking through a natural cubic spline interpolation example. If you missed our previous video on the theory of cubic spline interpolation, I will leave a link to that in the description down below for you. Before we jump into this example, let's quickly recap what cubic spline interpolation is. Cubic spline interpolation is a mathematical technique used to approximate a smooth curve passing through a given set of points. It's especially useful in situations where we have scattered data points and we want to create a continuous curve that captures a general trend. We can then use that curve to find valuable information about our data. Alright, let's take a look at our example. Here we have a set of data points representing the growth of a plant over time. Our goal is to interpolate a smooth curve that accurately represents the growth pattern between these supplied discrete data points. As you can see, we have 4 data points, and our task is to find the natural cubic spline that passes through these points. As we learned in our cubic spline interpolation theory video, we know that we were always going to have one less spine than our number of supplied data points. Therefore, with 4 data points, we will have 3 splines to fit cubic functions to. We also learned that for each spline we need to find, denoted by n, we will need 4n equations, such that we can solve for our 4n missing coefficients. Therefore, we have 12 missing coefficients, as you can see here. So, let's quickly make a plan of attack on how we want to go about solving this problem. First, we need to find 12 equations such that we can solve for our 12 missing coefficients. Once we have the 12 equations, we will plug them into a linear system of equations solver and then be complete with this problem. But stay with me and we'll walk through this problem fully together. So, let's begin working out how to find our 12 equations. As we learned in the previous theory video, we can get 2n equations through evaluating each of the 3 polynomial functions at our known data points. So let's just go ahead and do that. All we're doing here is plugging in our x values at our known points and simplifying. But to elaborate a bit more, we're going to evaluate our first polynomial with its 2 data points, so x1 and x2. p2 will be evaluated at x2 and x3, and lastly, p3 will be evaluated at x3 and x4. As you can see, when we are done here, this results in 6 of our 12 equations. Secondly, as we learned in the cubic spline interpolation video, we can find n-1 equations through the property of smoothness at our first derivatives of our interior data points, which in this example will give us 2 more equations as we have 2 interior data points, and you can see that here. Again, like we just previously did, we can do the same thing with second derivatives as we know we have continuity there as well. And this will also give us n-1 equations. To get the first equation here, we are going to take the derivative of our previously calculated first derivative of p1 and p2. Then we are going to equate them and plug in our x value where the continuity is occurring, which is x equals 3. This works out to the following equation, and I'm just going to rearrange it, such that all variables are on one side and the constant on the other side. Secondly, we can repeat this process with our second interior data point, between p2 and p3. Therefore, we will again take the derivative of our first derivative p2 and p3 functions we found earlier and evaluate them at x equals x3, which is 5. And again, we will rearrange this equation to put all variables on one side and just leave our constant, which is 0, on the other side of the equation. Now, as you can see, we have 10 equations and we are only missing 2. We were told to assume a natural cubic spline, so let's do that. In a natural cubic spline, we assume that the second derivative of our endpoints are both equal to 0, meaning at that point it is simply a straight line. So let's just go ahead and calculate the second derivative of p1 and p3 at points x1 and x4 respectively to get our remaining 2 equations. And again, just ensure that we are always rearranging our equations to put all our variables on one side, and we'll leave our constant, which is a 0 in this case, on the other side of the equation. Now that we have all of our 12 equations, we can solve for our 12 unknowns. To do this, we could try doing it manually. However, this would not be fun and take a while. Through using simple polynomials, we will always have linear equations, and therefore we have a system of linear equations. And from our previous lessons in this course, we actually know how to solve these. So I'm just going to write out our matrix so that we know what we are trying to solve. You can think of all these columns here as our coefficient values for each of our equations. And I will write this out here so that it's easier to visualize. Now, I'm going to use our Gauss elimination solver with partial pivoting that we developed in a previous numerical methods video. I will leave a link to that video also in the description down below if you missed it. However, there are systems of linear equation solvers online that you can find by Googling them. Now that we're inside Python, I have opened the Gauss elimination system of equations solver with partial pivoting. I took a minute already and entered our square matrix we just wrote down and entered in our variables and constant matrices here. We just need to call our function and insert our variable matrix and then our constant matrix and run the program. And as you can see, we have now solved for our 12 unknowns. Each of these x values represents a coefficient of our 3 interpolating polynomials. x0 is a1, x1 is b1, x2 is c1, x3 is d1, and so on. To visualize these polynomials, I'm just going to plot them rather crudely inside of Microsoft Excel, keeping in mind our domains that we have talked about previously. As you can see, this results in the following very nice smooth function. Now, back to our blackboard, we can now solve the second question we are being asked. We were asked to evaluate the interpolating polynomials at inputs of 1.5, 4, and 7. Quickly, I'm just going to write out our polynomials and their respective domains. For an input of 1.5, we are going to be using our first interpolating polynomial based on our domains. This results in an output of 1.876. Secondly, for an input of 4, it falls on our second interpolating polynomial, which has an output of 5.9. Lastly, for our input of 7, we will use our third and final interpolating polynomial. This results in an output of 10.58, and we have now answered all the questions that we are being asked. Hey everyone, in this video, we're going to be walking through a clamped cubic spline interpolation example. If you missed our previous video on the theory of cubic spline interpolation, I will leave a link in the description down below for you. Before we jump into the example, let's quickly recap what cubic spline interpolation is. Cubic spline interpolation is a mathematical technique used to approximate a smooth curve passing through a given set of points. It's especially useful in situations where we have a scattered data set, and we want to create a continuous curve that captures the general trend. We can then use that curve to find valuable information about our underlying data. Alright, let's take a look at our example. Here we have a set of data points representing the growth of a plant over time. Our goal is to interpolate a smooth curve that accurately represents the growth pattern between these supplied discrete data points. As you can see, we have 4 data points, and our task is to find the clamped cubic spline that passes through these data points. And we are also told at our endpoints that we have a derivative of 4. As we learned in our cubic spline interpolation theory video, we know that we will always have one less spline than our supplied number of data points. Therefore, with 4 data points, we will have 3 splines to fit cubic functions to. We also learned that for each spline we need to find, denoted by n, we will need to find 4n equations such that we can solve for our 4n missing coefficients. Therefore, we have 12 missing coefficients as you can see here. So, let's quickly make a plan of attack on how we want to go about solving this problem. First, we are going to find 12 equations such that we can find our 12 missing coefficients. And to find them, we will plug our 12 equations into a linear system of equation solver and then complete the problem. But stay with me and we'll walk through this problem fully together. So, let's begin by trying to find our 12 equations. As we learned in the previous theory video, we can get 2n equations through evaluating each of our 3 polynomial functions at our known data points. So, let's just go ahead and do that. All we're doing here is simply plugging in our x values and simplifying. But to elaborate a bit more, we're going to evaluate our first polynomial with its 2 data points, so x1 and x2. P2 will be evaluated at x2 and x3, and lastly, P3 will be evaluated at x3 and x4. As you can see here, this results in 6 of our 12 equations. Secondly, again as we learned in the cubic spline interpolation theory video, we can find n-1 equations through the property of smoothness at our interior data points through equating our first derivatives, which in this example will give us 2 more equations as we have 2 interior data points. So, we simply find the derivatives of our polynomials with touching interior data points, and then evaluate them at that input. And here are the 2 equations that we get from this. Likewise, we can find n-1 equations from doing the same thing with our second derivatives. As in cubic spline interpolation, we have smoothness at both the first and second derivatives. Then we are going to equate them and plug in our x values just like we did earlier. And here it is x equals 3. This works out to the following equation, and I'm just going to rearrange it such that all variables are on one side and the constant on the other side of the equation. Secondly, we'll repeat this process for our second interior data point between P2 and P3. Therefore, we will again take the derivative of our first derivative, P2 and P3 functions we found earlier, and evaluate them at x equals x3, which is 5. And again, just rearranging and putting everything to one side, and it results in this equation. Now, as you can see, we have 10 equations and are only missing 2. As we were told earlier to use clamped cubic spline and our instantaneous rate of slope at both endpoints is 4, we're going to use that now. In a clamped cubic spline, we'll use some known facts about the rate of change at the endpoints of our interpolating function. As we were told in the beginning of our question, assume that the rate of change at points x1 and x4 are 4. So let's just go ahead and use our previously calculated first derivative of p1 and p3 at points x1 and x4 respectively, to get our remaining 2 equations. Now that we have all of our 12 equations, we can fully solve for our 12 unknowns. To do this, we could try doing it manually. However, this would not be fun. Through using simple polynomials, we will always have linear equations, and therefore a system of linear equations. We can use our linear system of equation solvers that we have developed in the past. So let's just write out our matrix so that we know what we are going to be trying to solve for. You can think of these columns as our coefficient values for each of our equations. And I will write this out like so it's easier to visualize. Now, I'm going to use our Gauss elimination solver with partial pivoting that we developed in a previous numerical methods video. I will leave a link to that video down in the description down below if you missed it. However, there are also a system of linear equation solvers online that you could find by Googling them. Now that we're inside Python, I have opened the Gauss elimination system of equation solver with partial pivoting. I took a minute already and entered our square matrix we just wrote down and entered it into our variable and constant matrices here. Now, we just need to call our function and insert our variable matrix and then our constant matrix and run the program. As you can see, we have now solved for all of our 12 unknowns. Each of these x values represents a coefficient for our 3 interpolating polynomials. x0 is a1, x1 is b1, x2 is c1, x3 is d1, and so on. To visualize these polynomials, I'm just going to plot them rather crudely inside Microsoft Excel, keeping in mind our domains that we talked about previously. As you can see, this results in the very nice smooth function. In the previous video, we were asked to interpolate over the same set of data as we did in this video. However, in that video, we were using a natural cubic spline, whereas in this video, I wanted to use a rather extreme example of a clamped cubic spline to show you how they vary visually. As you can see in the clamped cubic spline example, since we set the first derivatives at the beginning and end rather steep at 4, the polynomial functions need to contort themselves to achieve the smoothness and continuity throughout the length of the interpolating polynomial. I hope that this video helped your understanding of how we go about solving a clamped cubic spline interpolation problem. If you enjoyed, please like, subscribe, and consider checking out our YouTube memberships by clicking that join button down below. However, if you have any comments, questions, or concerns about the information I provided in this video, please leave a comment down below and I will do my best to address your concerns.